Great. So let's start with the PowerPoint material. I hope you had a great week last week, and that you got a full, say, beginning on all your classes, your activities. And I also hope that your exercise or practice lessons were very, say, uh, beneficial for you in terms of what we are doing here. I know that there is a lot of opportunities to attend these kind of lectures, practice lectures. So don't waste time and attend those lectures, because many of the hints to solve the problems for the exercises and for the exam itself, you could get it from those practice sessions. This week is a time to see. Okay, I got a question here. The exercises of week 1 are graded. That I don't know. I believe they should take about some time before you submit those exercises. And the reason for that is that the grading is done basically by the teaching assistants and supervised by the main lecturer, but it would take some time. So just be patient about that, and you'll get your grades. As mentioned last week, so the content on this course is, say, put together in a way that one topic builds on top of the previous one. And this is the case, for example, for equilibrium of a particle. So everything we did last week related to dividing force vectors and into their components according to our reference systems, in this case, an X and Y reference system, then that's going to be essential for the topic we're going to see today, which is equilibrium of a particle. And in that sense, as engineers dealing with forces or design equipment, structures, or any mechanism that depends on forces, most of us are going to be dealing with equilibriums of a particle or equilibrium of a rigid body, but with equilibrium, because that's kind of one of the main or essential starting points for any designs that you're going to see in the future. Being able to calculate the equilibrium of any, say, physical element that you are working with is essential to any process or design process or creation process in the engineering world, at least in the mechanical engineering world. So this week is going to be related to equilibrium of a particle. It's a pretty simple concept, yet it could bring some challenges if we are facing, for example, some sort of a case where we are handling multiple or many forces applied to a specific body or particle here. In any case, this is analytic. We're going to do it by hand, so it's not expected that the cases are not going to be complex. They're going to be fun, but they're not going to be complex. Let's jump to the next slide. The aim of this lecture today is going to go over these 5 points. And I would say that the first 2 are conceptual ones, where we're going to lay out the foundations to what's coming next related to how to apply this concept of equilibrium of a particle. And the first one of it is the free body diagram. Maybe some of you have heard of this concept of the free body diagram, many of not, but it's a pretty simple concept, and yet it's pretty powerful, because from the free body diagram, also abbreviated as FBD, stems all what we're going to do in many of the courses. Free body diagram, we're going to explain what it is, and then how can we use the free body diagram to write down the equations of equilibrium, or equilibrium equations, how you want to call them. And then having written down those equations of equilibrium, then how to find out what we need to find out, which is basically to know if the system we are witnessing, or we are that is in front of us, is in equilibrium or not. Then we're going to see where are the useful applications, but from my own experience, I would say that applications are many. So we will fall short trying to number all the applications where we can use this concept of equilibrium of a particle. And then we're going to go over some examples. Time provided, so we are also going to go over more, say, specific examples, or a little bit more examples that carry a little bit of more complexity. They are fun also to solve. Practically might not be something that you might face in reality, but in the academy, they are very, let's say, fun, because they cover most of the concepts that we're going to see here. And makes us think about how to tackle this problem, or how to solve this. Let's see our first concept about the free body diagram. You might have read already this material, but I want to give you the short and say digested version of what is a free body diagram. So when you're studying something, call it a particle. Call it a body, rigid body, flexible body, or anything, structure, anything you're designing. When you want to know what's happening with that physical element, what you do, or the first, let's say, step you take to get to know what's happening, is you try to isolate that element from the world. Let's put it in that way. And as it is written there, so what you do is, for example, now that we're talking about a particle, you take that particle and then you forget that everything else exists. And then you just you consider only the forces applied to that particle. So you don't pay attention, you don't care if there are many other particles around it, or if that particle is attached to something else or anything, nothing. So you just isolate that element, and then you draw on that element what are the forces applied to it. It could be one force, it could be many forces, it could be, and if we're talking about particles, remember, particles are not subjected to moments. Particles are just subjected to forces. And the clear definition for that is that the concept of a particle is something that doesn't have any dimension. So, and if it doesn't have any dimension, then you cannot associate any rotation to a particle because of that. So basically, when we talk about a free body diagram for a particle, the only thing, or the only, say, elements that can exist is the particle itself and forces applied to the part. And yeah, so we isolate that, and that's it. And this is, if we take this from a higher level, meaning, okay, the concept of a particle, but, can we, draw a free body diagram of a car, for example? Yes, we can do it. Can we draw a free body diagram of an airplane? Yes, we can do it. So what's the level of detail we can of that? So because, for example, depending on what you want to investigate on the item, depending on what you want to develop for or design for example, if I'm going to try to draw a car, a very bad drawing of a car. So you could say, well, yes, you have a car, and then I isolated the car from the ground and from everything. I know that they are going to have some forces, due to the tires in contact with the ground, with different. And then the car has a weight, and maybe the wind, when the car is moving in this direction, this is a velocity. Maybe we have a wind applied to, as a resistance force to the car, and so on. So depending on the level, and as it is a body, so we can do even, what are the moments applied to it or anything like that. But if you're only interested to know or study, for example, how the car, moves, what's the displacement of the car, meaning what's the velocity of the car, what's the acceleration of the car, and that's it. So you are not interested, imagine, on the reactions of the tires with the ground or the road or anything like that. You could easily oversimplify the model of a car by being a particle. And these particles, acting on this particle, are the force of the resistance force of the wind. You have the weight of the car concentrated in the particle, for example, and you might consolidate both forces acting, as resistances F1 plus F2, and then you say, well, and this is moving with a certain velocity here. So depending on the degree of detail you want to not understand, but use for your purposes on design or studies or anything like that, is the level of, let's say, it's going to be represented correspondingly in the free body diagram. Then what does it mean? That if you have the real deal, the real element here, which is the car, forces acting on a car might be, the number of forces acting on the real element, on the real car, can be thousands of it. I don't know, I cannot count it, because of the interactions between the internal parts of the car, interactions of the car with the surroundings and everything. But every time you take a step down here, you are just simplifying the complexity of the problem you have in front of you. So this is a high level of simplification you are, let's say, taken from the real to this, let's call it the rigid body diagram, or the free body diagram of this rigid body. And then this is way more oversimplified when you take it to the free body diagram of a particle. Then, as mentioned last week, so we as engineers use oversimplifications to try to understand what's happening and understand our designs. And we can do that. And we can do that to a level of success that we are going to be sure that our results, our designs, our resultant work is going to be, reliable, it's going to be safe, and it's going to do the job. And many people before us, they have taken care of, ensuring that how to go from a very well or let's say oversimplified model from, let's say, particle to the real deal or to the real application. So we can be confident that, we can succeed on this. Now, let's remember, the free body diagram is a nice representation of what's happening in reality, but it's not the same. It's just an equivalent model, and that's it. And we as engineers need always to understand that what we do is, we're just working with equivalent models. Why we do it might be because we are, let's say, ignorant of what's really happening in the physical element. We cannot explain physical, with physics, what's happening in there, the relationship between parts. But that's why, because of many things, we need to simplify our, say, approach to the study we are taking, or we're carrying out in any of these elements. Then definitely, when we talk about the free body diagram, we're going to be in the presence of a reference axis. So we're going to have this typical XY reference axis, and then we're going to locate in the center, the origin of this reference system, the particle, because now we're talking about a particle, and then all forces that are going to be applied to it, this one, or this one. It could be initially represented in the original orientations, but in the end, we're going to see that we need to use the very same concept we studied last week. And that is that we do understand that we need to work with components because it would make our life easier, just to get rid of the, these different orientations and try to normalize the application of the forces acting on the particle just based in two directions, and that's it. And how do I transform this working, isolating the particle, just leaving the forces acting on it, and then using the force decomposition that we saw last week to present what is the equation. And it's very simple as this slide is presenting it. So an equilibrium of something it can be static or it can be dynamic, and that's it. In this case, we're dealing with, or let me write it down here, because this is an important concept that we need to understand, that not because something is moving, it means that it's not in equilibrium. That's not the case. So I want to write it down here. The equilibrium, it can be static, something that doesn't move at all, or it can be dynamic. Yeah. Then we need to understand, grasp that concept that not because something is moving is not in equilibrium. No, it's not. That's not the case. And when you read this definition that is written here, for example, for a case, if our particle is at rest or moving at standard velocity, then according to Newton's law, the sum of forces acting on it is zero. I want to make an emphasis, open up a term here, so there is no confusion in something. So we understand that when something is not moving, it's because all forces applied to it, might not have any, say, dynamic effect on the particle. Hence, it's not going to move. Let's start by saying that, from Newton's second law, that forces, sum of forces equal to mass times acceleration. Now, let's put it in vector form here, because we don't know where those forces are going to push that particle, towards which direction is going to, let's say, they're going to push the particle. So I'm just putting vector form because of that, because we need to include the orientation of it. But now, if something is static, it means that this is not moving anywhere. So this is zero. And this is zero, meaning that, all the sum of forces are equal to zero. And this is interesting because for us, understanding this from our experience point of view, even without studying any engineering purposes, we might grasp intuitively that if something is not moving, it might be because even though I applied forces to it, it's not going to move anywhere. So it's just, standing the forces, it's just holding the forces. So all forces are like, canceling each other out, so it doesn't move, the particle doesn't move anywhere. So we may understand that intuitively, that, well, that's something that doesn't move, that is static. We might say that it's in equilibrium because all forces applied to it. When you sum all the forces, when you add up all the forces, then the resultant force is zero. And it has to be zero because that particle doesn't move anywhere. Now, the term I want to open up is this one, standard velocity. So forces applied to a moving object might be zero if you have constant velocity. That's the first thing. And kind of as a magnitude. And also if the movement is, if we're talking about particle, well, it's because if is displacing. So it is translating or is in translation. Now, when we get to the point, or you get to the point that you see the same type of considerations, but for rigid body, then, this is very key to differentiate that if a body is rotating, then, it might have constant velocity, but if the body is rotating, then, this does not apply. So it's a different thing. There is an acceleration, and then, we cannot consider that all sum of forces are equal to zero. No, all sum of forces are equal to something. So this is something that it is at the beginning a little bit difficult to say, well, but if velocity is constant, then it's not moving. No, it doesn't mean that it's not moving. It means that it's not in translation, it's not displacing. Let's put it this way, kind of, you can have a constant velocity and still be rotating and you're moving. So constant velocity doesn't mean that something is static per se. Just keep it in mind. This is a very important concept for us. So don't take for granted that if something is at constant velocity is because it's, it doesn't have any acceleration or anything. It might have acceleration. Okay, there's a question said, so basically it's moving but has no acceleration. Yes and no. Let me go ahead on an example and to give you some. Imagine that you have there is a center of rotation here, and you have a particle rotating around that center of rotation. Yeah. So you have this, imagine that this is, I'm just drawing kind of the radius of this particle at this moment. And this is something that I hope that you get to see, maybe mechanics too, I don't recall that. So there is a radius here, which is the distance between the particle and the center of rotation, and this particle is rotating here. Yeah, it is in rotation. It is moving. So now, so far we agree that if this particle is moving, is rotating around this point O, so it is moving. But what happens if the speed, the velocity here is equal to, is constant? So if it's constant, let me write it better. So this is V, magnitude is constant. So somebody says that the video is frozen. Is it? Somebody else says that it's okay. Okay, perfect. Okay, thanks for the feedback. Great, let's continue. So you have the particle, and that particle, thank you. That particle has a constant velocity, linear velocity. Even though it's rotating, you can have no constant velocity. The acceleration, I'm going a little bit ahead of the time and of the topics we're seeing, but the acceleration of a particle which is rotating around a circular rotation around this point O has two components. Has one tangential component, AT, and has one normal component. Yeah. The tangential component of the acceleration of this particle, or the tangential component of the acceleration of this particle depends on the change of the velocity with respect to time. Either one that's the one we know, that we have always seen in our high school courses. However, the normal component of the acceleration depends on the square of the velocity times r, something like that. So meaning there is still a rotational speed, there is still a radius, meaning that even though when the velocity is constant, you are going to have an acceleration, and the acceleration is going to be normal. This is going to be null, zero, but there is going to exist a normal acceleration. So again, that's kind of the concept of not taking for granted that if the velocity is constant, there is no acceleration. It might be acceleration depending on the type of movement that the body or particle is experiencing. Great, thanks. But this is ahead from I don't know if we're going to see it. Well, I'm just in charge of the first period, but this is the why of that. Again, this is something for life. Actually, no, it's not a astro. It's something for the future. Now, of course, if I then came to the conclusion that something, let's call it static, and the sum of forces acting on it are zero, or is zero, then consequentially, if I take the components of those forces, it must be that the components also, or the sum of the forces in x direction and the sum of forces in y direction, they need to be also zero to comply with these thing here. So when we talk about equations of equilibrium, we are talking about this. Basically, these two things here, that we say something is in equilibrium if static equilibrium if the sum of forces in each direction of both components are zero. Yeah. And just a brief, what is a dynamic equilibrium? Well, dynamic equilibrium simply says that you've seen this, that sum of forces equals to mass times acceleration. Let's put it in vector. This is an equilibrium. So the only thing that you're saying is that there are forces applied to the particle or to the body, but those forces aren't, the resultant is not zero, the resultant is something else than zero. So that's what we call dynamic equilibrium. And remember, most of the things we see in kind of as physical elements, constructions, designs, machine elements, machinery, mechanism, everything, most probably they are in equilibrium because some forces are acting on it and there are consequences to the application of those forces. So meaning that there is a nice physical relationship between what you're applying on top of that and then what are the consequences. I take on this point, let's say a great deal of it. I take it a lot in engineering mechanics 3, where what happens when you apply forces on an element. So what is happening internally to the material, let's say to the steel, to the aluminum, or anything. So what's happening inside of it? How was the response of that material body to the application of those forces? It's a pretty interesting concept, actually. It's pretty simple, but pretty interesting. It says here another question. With rotational movements, what is the force that counteracts the centripetal force so that the sum of forces is zero? Let me understand this question. Okay, yeah, that's a nice question. Yeah, so definitely when you are in this case here, if there is if there is nothing that is, let's put it, physically keeping this particle from going out, so of course it's not going to be in circular motion. So of course there is a force here that is going to try to move to hold the particle here. And without going into very much in the explanation of this, I want you to consider this let's say this concept, or this my own definition of what are these three magnitudes as. Let's call it position, velocity, and acceleration. So if I wanted to give a very my own terms of the definition of these three concepts, position is where something is. Position is very clear to everybody. So position is, well, the particle is here, or the particle is here, or the particle is here, and so on. So position is something. It's something that it is time dependent, or it might be time dependent. So it says, this particle is right here, right now, measured from this reference system, and that's it. So this is very clear. Now consider my definition of what is velocity or acceleration, or how do I see it, or I have seen it for many years, and that's helped me a lot to understand many concepts in dynamics. Velocity is the direction or where the particle is going. Yeah. So if you have a car, and that car has let's say speed in this direction, so the velocity says where at that moment the car is going. So that's clear also. So position, where the car is, velocity, where the car is going. But now, what is acceleration? As you can define, well, yes, acceleration is, is a derivative of the velocity with respect to time. Well, yeah, but that's mathematically. But for us, if we wanted to grasp a physical concept out of it, I wouldn't use this one. For me, acceleration tells you where the particle, or in this case, the car, would like to go. Imagine that you have the car here. This is the velocity of the car. But there is a negative acceleration because, you're applying forces. and the car is decelerating. Acceleration, as I have defined it, previously, and it has helped me understand most of these concepts. Acceleration physically tells me where the particle or element would like to go. It's not going, but would like to go. Again, position, where the particle is, velocity, where the particle is going, and acceleration, where it would like to go. Now, this here, kind of to bring it down to your question, then yeah, we understand that if we put certain kind of rotation in here, then the particle, might want to go out of this. But then a force associated with the mass of that particle is the one who would say, you know what, this normal acceleration of the particle, which is, rotating in circular motion, points towards the middle of, or towards the center of rotation, yeah? Then this is where the particle would like to go. And this is sort of, counteracting where the particle really kind of, if you let it free, if you eliminate this normal acceleration, it will go somewhere. But more or less, this is kind of, the workaround to answer your question that you asked. I hope it makes sense a little bit, because let's say I'm talking about, this concept without, providing you with more basis about what we're going to do here. But yes, there is always something holding so the particle doesn't, go anywhere. But again, 2 steps back. If the velocity is constant, it doesn't mean that it doesn't have acceleration, because acceleration may have 2 components, and just consider that. I hope it makes sense, what I mentioned here. So it says that when there is rotation involved, acceleration cannot be 0. Yeah, practically, pretty much. That's a pretty nice, let's say, summary of that. Yeah, that's meaning that sum of forces is larger than 0, or the sum of forces isn't 0. Yeah. Okay, let me go back. So when we talk about equilibrium, we talk about static or dynamic equilibrium. Okay. So when we talk about equilibrium, definitely, without any doubt, sum of forces equal to 0. When we talk about dynamic equilibrium, then the sum of forces is not equal to 0, it's equal to something, as one of you wrote down in the chat. Yeah. So when something is moving, then we're talking about dynamic equilibrium. And yes, forces are not equal to 0, because you have this, let's say, law of life to let us know that, if it's moving at some point, in a circular motion, it might be that, there exists this dynamic equilibrium. Right? So I want just to make emphasis. Regardless, they're talking about static or dynamic equilibrium, I just wanted to keep in mind all the time that if you have a constant velocity, it doesn't mean that it doesn't have acceleration. That was kind of my point on here. But study the case, study how the particle is moving, how the body is moving. If it has acceleration, then we're talking about dynamic equilibrium, because we have to comply with this formula here, with this law. If it's not moving, then we're talking about static equilibrium. And then, you might start, okay, what happens if it's moving in rectilinear motion? Well, in rectilinear motion, it's moving. Yeah, that's correct. But then, if we take a oversimplified, let's say, a free body diagram of it, where, the velocity is 0, then in a rectilinear movement, the acceleration is definitely 0, because there is nothing there. There is no other component. It's just the same component. And then you may treat this as let's say, a static case. It's moving, but you might treat it as a static case, because let's jump to I believe it's the 3rd law of Newton, where, if there is no action, there's no reaction, but, if you have any forces applied to this particle, so those forces are not doing anything to change the status quo of the particle, and the particle is moving with a constant velocity here. So if the velocity is constant, then the acceleration is 0. Another comment, but dynamic equilibrium means that the forces acting on the object equate to 0, despite having a constant velocity. Isn't that the definition of equilibrium? Dynamic equilibrium, remember, again, many things we see in life are always in equilibrium, even though they're moving. So dynamic equilibrium is, when you need to, let's say, forces are not strictly equal to 0. They are equal to something, like in this case, mass times acceleration. Actually, if we wanted to extend the full vocabulary that we're using here, when we talk about this formula, these are external forces. Just, follow me. These are external forces. These are also forces. That's why this is a dynamic equilibrium. We talk mass times acceleration. These are called inertial forces. So when there is the existence of inertial forces, then we're in the presence of a dynamic, or we might be in the presence of a dynamic equilibrium. So that's why, these are forces. Forces equate to forces. But these forces that we know, mass times acceleration, we call it, or they are known also as inertial forces. And then we are in dynamic equilibrium when external forces equal inertial forces. I hope that brings a little bit of light to the discussions we're having right now. We want to study a particle or forces acting on a particle. We want to determine the equilibrium of that particle is in equilibrium. That most likely, most of the problems we're going to do now is to guarantee that the particle, or certify that the particle is in equilibrium. And then, we take the particle, draw the free body diagram of the particle where all the forces are acting. We separate those forces into their components, x, y, according to the Cartesian axis, this is xy axis. And then we apply the equilibrium conditions, equation of equilibrium, which are, fx, sum of fx equal to 0, and sum of fy equal to 0. Yeah? And then What's called the analytical solution? The analytical solution means that when we separate those forces into their components, it might be that if we are trying to figure out if the particle is in equilibrium, then just by the application of these two formulas is more than enough, just to validate that something is in equilibrium. Because, if I have, for example, a particle, and then you have three forces. You have three forces, F1, then you have F2, and you have F3, and then you have XY. If you say, well, is this particle in equilibrium? So you want to validate that this particle is in equilibrium. Well, you just apply the sum of forces in X equal to 0, verify that this is met, and then you also verify that the sum of forces equals to 0. If the verification passes, then you can say, yes, it is in equilibrium. But that's not the case we're going to see here. What we're going to do is that I'm going to, as the exercises are already drafted and the whole content is drafted here. So our job in this particular lecture is to find out something like this. So I have F1, I have F3, and now the question would be, tell me the value. Okay, this is known, this is also known, but then you have this force here that is unknown. And the question would be, tell me what's the value of this force so this particle is in equilibrium. So then it makes a little bit more complex, because it's not a matter of verifying, but now it's a matter of, let's say, finding out which value of the force would make the whole system be in equilibrium. And when we do that, meaning that when we postulate these two equations, to find out now the value of this unknown, we might be facing something that, we have, let's say, we don't understand. We have, how to rephrase it. So we're going to be in the presence of something that they're calling here analytical solution of the equilibrium conditions. And that means that by having at our disposal, these two equations, F1 and Fy, Fx and Fy, is how do I use those two equations to find out the value of F? And then, as I'm already using the term equation here, so we are then now analytical solution, let's put it in this way, might be a synonymous of solving system of equations, where now you have two equations, this sum of Fx and sum of Fy, trying to describe the same phenomenon, and then those two equations form a system of equations. And then by solving that system of equations, you're going to try to find out the value of F. And this is where the complexity starts increasing. If I abstract a little bit from all of these, there's a maximum here that we need to have present all the time, that if we're solving a system of equations, the ideal case would be, or the typical case would be, that if I have two equations, which are this sum of F in X direction equal to 0, and sum of F, we write it correctly here, sigma Y, that if I have two equations, the maximum number of unknowns must be 0. If I want to have success in solving that system of equations. So this is kind of the optimum case. So during the resolution of the problems or examples we're going to see here, if we find out that we have two equations, that we have two unknowns, then for sure there is a solution, or most probably there is a solution to that system of equations. It might be the case that you have just one unknown, but if you find yourself in the position where you have two equations only and you have three unknowns, then that system of equation is not solvable by typical means. Of course, we're going to present other equations that we could integrate to our system of equations so we can match the number of equations and number of unknowns. I hope that this concept of number of equations equaling the number of unknowns is familiar for you, because that's kind of what would allow us to have certain degree of success in solving this system and finding out eventually kind of what we want to find out. That might be the magnitude of the force, or it might be the orientation of a force, or it might be both. Again, it's nice to remember that these equations that are highlighted in yellow are part of your formula sheet that you have access to. So this is going to be with you during the exam. So you're going to have access to that. So no need to memorize any formula in here. Useful applications. Here in the material is listed a few applications of where, okay, I got a question or a comment. Let's see, the first formula is basically the formula to find the magnitude of a vector. Yeah, that is correct. Yeah, which is I don't know if you refer to this one or to this one here, but let's put it this way. This formula here, this sum of forces as a total, let's say, big title here, big F. Yeah, it basically comes from this, and this is derived from the Pythagorean theorem, when we're talking about two vectors in a Cartesian coordinate system, x, y. And this is what we saw this is actually what we saw last week, the resultant of a force, and then this is the angle, of that resultant. And remember that the angle always measures with respect to the x-axis, as per convention, what we have been using since last week. All right, so useful applications. Here I listed some, but I would say that in our, professional life, and if you see standards, design standards, if you see design procedures or methods, anything, most of those methods they start from the equilibrium considerations, or let's put it, equilibrium considerations. So, and more specifically, if we're talking about structures or static elements, everything originates from it, from finding out the equilibrium, finding out, why it's in equilibrium, what are the forces applied to it, and then, everything explodes from it. So when we talk about useful applications, most of the things engineers, or I keep referring to mechanical engineers, but because that's the experience I have, but in many fields of engineering, you're going to find out that most of the things stems from equilibrium. And yes, here I've written some, for example, we can try to understand or analyze or study knots, rings, pulleys, anything. We can consider, even though it's here, that large object, we can consider, for example, big cars and airplanes as particles also. But, the good thing about how the program is structured for this course is that, we take it easy the first time. And it may be boring, the first 2 lectures when we see about, force decomposition and equilibrium of a particle. But it is important to refresh those concepts to move forward in what we have to offer you. Definitely, there are thousands of applications. And one of that is interesting for us to show you is the application of these equations, but in the case of springs. Of course, we're going to see ropes, cables, eye bolts, or any other type of elements, but springs, let's say, bring to the table an important relationship. And that is that how forces are, let me try to put it this way, developed in springs. So a force, as let's say, if I have a spring attached to a wall here, and this is a spring, and this on this spring there are no forces applied. So just a spring is resting there. So this spring has a nominal, let's say, an initial length. But if I stretch this spring, let me try to make a copy of this so it looks more or less similar. Just a second. I'm going to answer, just let me finish this one. So, and then I stretch this one here, and it's heavily stretched. So, because you can pull that string. So, this difference from, actually, let's put it in another color. I will come back to the comment just a second. This difference in the length after you stretched that spring called S, the force that you're going to be, imagine that you try to pull this spring. So the force or that you're going to feel in your hand while trying to pull the string is going to be proportional to how far or how much you stretch the spring. And that's going to comply with this formula here, where S is a stretch that you're applying, and K is a construction constant that is natural from the spring, and it's called the stiffness of the spring. And that's particular from the spring, from any spring. And the multiplication of both of those terms will give you that force that you're feeling in your hand. Let me make a pause to go see the chat to see what's... They said, sorry to go back to this, but is constant velocity and startup velocity the same thing? It's not. It's not, and I cannot answer why, let's say, it's written as standard velocity. I would need to ask to Olli-Pekka. But that's why I wanted to make emphasis, so there was no doubt that, we are talking about constant velocity here. So this is something that I would need to ask from Olli-Pekka to validate if the terminology that he's using corresponds to this. But, I want to bring out this just to make sure that we are on the same page with the physical aspects of the movement of something that is called something in equilibrium, or something where I could apply this formula. But that's the short answer to it. Okay. Yeah, that's why I wanted to open up this term, because for me it's something, well, maybe the terminology he's using. You're going to have available a recording of, by the way, the recording I did last week. Unfortunately, there was a problem and it was corrupted. I don't know what happened. I hope that it doesn't happen the same this time, because I would like to publish this recording so you have access to it and you can go over what we discussed today. However, you have available, or you're going to have available, Olli-Pekka's recording of this lecture, meaning that he has his own recording for this, and you could also kind of verify from that recording. So when he comes to this flag, so what is this? But I hope that you can have, at least you're going to have access to Olli-Pekka's recording of this lecture, or of a lecture, or for this type of lecture, or this lecture specifically for this topic. But also I hope that I could post the one that we are doing right now, so you can go over all these, comments, discussions, and explanations. Thank you. Anything else regarding to standard velocity or constant velocity? All right. So we were here with the spring, and yes, the spring brings to the table maybe another equation that we might need if we're in the case where the number of equation is smaller than the number of unknowns. And that might happen on when we are dealing with spring problems. So this is important to know. I bet this concept is familiar for most of you, but it is worth kind of remembering of what's the force. Again, the analogy that I used here was that you have a spring attached to the wall, and then the spring is at rest, meaning that you are not stretching the spring. But then when you start stretching the spring, as soon as the stretch or this S here starts increasing, you are feeling certain resistance from the spring. And that resistance, let's put it in that way, is measured by this, let's say, relation here, K times S. So the longer you stretch the kind of spring, the more resistance is going to oppose it there. And that resistance is going to be, let's say, based also on a construction factor of the spring called K, which is the stiffness of the spring. And it depends on the manufacturing characteristics of the spring. We're talking about material, geometry, and so on. So in here, most of the time, K is going to be given as a constant, something, you have this problem with several springs, and the stiffness coefficient of each of the springs is this or that. And then you can use this formula in your, say, solutions. But again, I think that this concept is pretty familiar to most of you. Great. This is a nice discussion. The content of the theory seen so far is short, but the discussion has been great. But let's jump to the examples now. And this is one example. When you read it, you're going to be associated with something that I said that. Now, it's not a matter of verifying that the particle is in equilibrium, but they're saying the particle is in equilibrium, but please tell me what's the value of a force to make everything comply with that equilibrium condition. So let's read it. It says, determine the magnitude and the angle of a force F1 in such a way that the particle is in equilibrium. So now, we are talking here about determining the magnitude and the angle theta of force F1. So let's see. Now, they are already telling me that there are two things in this problem that we don't know. And then I don't know how much is the magnitude of this force, and I don't know this angle here. So now, just in the description of the problem, I have exhausted the amount of unknowns according to the number of equilibrium equations we have. And let me go back to it. So if I have, this is the first unknown, this is the second unknown, you can interchange this, doesn't matter, it doesn't affect the result. But then if I have two equations, then again, the maximum number of unknowns that I could have in my system of equations is 2 if I want to have any success at solving them or finding them. So now the description of the problem, I'm already knowing that there are two things that I need to find out, this one and this one. So it most probably fit the description, let's say the solution process that I'm going to use here. But yes, I have two equations and two unknown. It means that this might be solvable, right? So look at the amount of information that the postulate or the description of the problem is giving you. So let's continue. Again, so first step, let's divide the forces into all components. So we have force 1, 2, 3. I have all the conditions to know the components of force 2. I have all the conditions to know the components of force 3 because I know the magnitude and I know the orientation of each one of them. And remember the convention we have been using, which is at all angles or these forces, we would like to measure them with respect to the x-axis all the time, so we have a consistent, let's say, way of representing what is a component in x and what is a component in y. But remember that if we use this convention, we always need to validate that which is the final direction of that component. Is it a positive direction because it points toward the positive side of the Cartesian axis, or it is a negative, let's say, direction, because it might be that because of the convention we are using, that doesn't come along in the when I'm kind of decomposing the force. So I always need to verify that what is positive and what is negative. Definitely, in most of the cases, if I use this convention of using of referencing any force with respect to the x-axis, like the angle less than 90, so most of the results are going to be positive. But we always need to verify in the end, after I have decomposed the forces, what are positive and what are negatives. Let's continue. With force 1, definitely, I'm going to have these two components. I will incline because of the orientation of this, but I'm going to have the horizontal component of x component in here, F1x. And this is slow. So I'm doing it with the math. Okay, like this. And this is going to be the vertical component of it. Now notice that here they're represented as positive. As I mentioned, I just want to emphasize this so there is no confusion. These are represented as positive, maybe positive terms, but this force is in the third quadrant of this reference system. And in the third quadrant, pointing downwards means that both components are negative. But this is clear that the components of this F1 is a horizontal component, magnitude times cosine, the vertical component is magnitude times the sine of the theta here. Then force number 2, again, this is a very nice example because we have two ways of how we could represent angles or orientations of forces on a reference system. So in this case, the orientation of this force 2 is represented by this rectangle triangle here, or straight. Yeah, that's where in this one here. And then if I want to know the kind of just as a refresher, if I want to know the x component of this force, I just have to multiply it by 5 divided by 13. So this would give me the horizontal component. And then if I want to know the vertical component of this force here, I will have to multiply that magnitude of 300 times these two, times the relation between these two, or the division between those. That's what you have here. And this is the easiest one that we are all known, kind of used to, is that, what's the component of this component? What are the components of this force? Well, use the cosine of 20 for the horizontal component and use the sine of 20 for the vertical. Then calculate the resultants in x and y direction. You see F2, this is positive, positive. F3 is positive, F1 is negative. F1 in vertical is negative, F2 in vertical is positive, and then F3 in vertical is negative. So you see, that's why in x direction we have F2 plus F3 minus the F1, the one that we want to know. And then when we substitute all the values that we have found previously here, so we are going to end up with this relation. That the sum of forces in x equals to this one thing here, and this equals to 0. Now, can I solve that equation? Well, evidently I cannot do it because I have one equation so far and two unknowns. Let's move forward here. If we do the same with the vertical or y direction, again, I'm going to have the only positive is going to be F2, and then the other two, remember, they're going to be negative. So F3y and F minus F1y. If we substitute everything there, so we are going to end up with this formula here, which says, okay, now this is the sum of forces in y direction. This is the sum of forces in x direction. And remember, as they're saying that this has to be in equilibrium, the sum of these, the resultant of these components must be 0. Then we have one equation here, and we have one equation here, and we have one unknown, two unknowns that are repeated here. So two equations and two unknowns, meaning that most probably we're going to be able to solve this system of equations. Here they are gathered together. We know that both resultants have to be 0, must be 0. And the reason for that is because the problem is saying P is in equilibrium. That's the only word we need to add this 0 here. Then if we continue, there are several methods that we could use to solve equilibrium system of equations. As mentioned in one of the slides before, if you had time to browse it or read it, mentioned that if you have a smart calculator, you can input those two equations and then, they would give you the results right away. If you don't have such a calculator, don't know how to use it yet, well, there are manual methods, let's put it in that way, that we could use to try to find out those values. And one of the first ones is substitution. And substitution means that, we take one of the variables from one side and try to replace it, substitute it in the other side. For example, in this case, if I kind of focus on equation 1, I can isolate F1 from this equation. So if I move, for example, 538.25 to the other side, I'm going to answer that question right away. Just a second. Move this to this, and then I move the cosine of theta to the bottom. I end up with this. Now, regarding, to be sincere, I think you can use it. I can write the question down and answer. I think. Let me see. I would give me just a second. Let me try to search for something here to try to find an answer. I'm looking on an old exam because in the exams, Olli-Pekka always mentions the kind of the requirements for the exam. Let me see. I don't have it, but if actually in one of the demo lectures that you're going to have access, he mentions that most of the examples we're going to be seeing here, or you're going to be doing here, are pretty much solvable by hand, meaning that there is not this degree of complexity that you would really need, to use a smart calculator. But I will ask and come back to you with that information. There, no problem. Now, if I have isolated from equation 1 the value of F1 that is still in terms of the angle theta, then what I can do is take this value of F1 and input it in equation 2. Then if I do that, what is going to remain is an equation that has only one unknown, and that unknown is the angle theta here, as you can see here. So you have one equation and one unknown. If we keep moving forward, then a little bit of manipulation here. So you take, sine divided by cosine is a tangent, rearrange everything, and then you take the inverse of that tangent, and it tells you that the angle of that force needs to be, as a first, say, answer to the question that they are being asking here, has to be about 12.19, put it 13 degrees, what? Well, 12.19 degrees. And now that I have the value of that angle, I can come back here, write that value of the angle in here, and it would give me then the value of the magnitude of F1, which is going to be, for this case, 552 newtons. So for this system, for this particle with three forces acting on the particle to be in equilibrium, it means that this angle has to be 12.9, and this has to be about 552 newtons. By doing so, this is equilibrium. And these are the answers, kind of that, to the questions postulated before in the description of the problem. I believe it's important to emphasize here that if you write 12.85, it's okay. If you write 12.95, 94, or something like that, it's okay. So it's not going to be much big of a deal here, as long as it's not 15 or something like that. So don't stress out about these significant figures at this stage. Actually, when I discussed with Olli-Pekka about these significant figures, he pretty much was a little bit against using it because of certain physical discrepancies that you can find when trying to express results of a physical problem. And I agree with him, but that's another thing. But that's why no rigidity on using decimals or this kind of stuff. If you want to make sure, well, as I mentioned, use 4 decimals. What questions do you have? Let's then jump to the other one. Interesting. This example says the device shown is used to straighten the frames of wrecked autos. Determine the tension of each segment of the chain. So we have a chain here, which is the one starting at A, passing through B, and ending in C. If the force which the hydraulic cylinder DB exerts on point B is 3.5 kilonewtons, as shown, this one here. Okay, so what is being asked in this problem? So if I try to figure out how these forces are acting with respect to let's imagine a particle on point B, then I could say that, well, I know that there is a force that is trying to pull this particle towards the car, this one here, and there is a force that is trying to pull this particle towards point C, because the cylinder tries to push the particle in this direction, but then these two are kind of resistant forces, so they are trying to avoid that the particle moves in this direction. That is very good. Now, again, it's not mentioned here, but the assumption is that the particle is in equilibrium. And then now say, okay, but if I want to, as an analogy, try to find out how many unknowns I'm going to have here, as we did it with the first example, that in the first example, the unknowns were the magnitude of force 1 and the angle of that force with respect to the x-axis. So what is here? Well, basically what they're saying is, okay, I need to find out the magnitude of this force, and I need to find out the magnitude of this force. Then they're not asking for orientations or anything, because actually orientations are given in the figure shown here. Meaning that so far I have figured out that I only have 2 unknowns that I need to find out, and then now using this equilibrium condition, or system of equilibrium of a particle, system of equilibrium of equation of equilibrium, then it means that I might be able to solve this system and give answers to how much is the magnitude of FAB and how much is the magnitude of FBC. No orientations, not needed, because orientations are already given, they are already fixed. And they are given by these values of, this 400, for example, the point of application in vertical direction, or of this B with respect to C is 450 millimeters, and then 250 millimeters in the horizontal direction. And then if I wanted to know the orientation of this hydraulic cylinder on how it's acting at the moment, then it would be 400 millimeters in the horizontal direction and 450 in the vertical direction. Now, what happens with force AB? Well, force AB is horizontal, meaning that I already know what's the angle that forms with the x-axis, which is 0. First step for all these problems is to solve or to draw the free body diagram. Again, we are taking point B as particle, let's put it in that way. I know the particle, the force exerted by the hydraulic cylinder forms an angle alpha with respect to the x-axis here. I know that the force, counteracting this hydraulic cylinder, this force BC, forms an angle of beta angle with respect to the x-axis. Do we know how much those angles are? Well, short answer, yes, because we have those distances represented in the figure there. With just a little bit of trigonometry here, we can know right away how much is angle alpha and how much is angle beta here. So if I wanted to write it down, so this would be something like, let's see how much decimals he's using here. So no worries about that. So 48.366 degrees, and this one would be 60.945 degrees. So this is the way it's represented here. Now that I have the free body diagram, I have figured out how much are those angles there. Then I can write down the equations. In x, I know that it's going to be, I know that this is negative because it's pointed to the left here, according to the conventions of a reference system. The component in x of this BC force is going to be positive here. And the component of the hydraulic cylinder force is also going to be positive here. So meaning that I have BC, this one here, positive. I have this hydraulic cylinder, positive, minus this force here that is acting. And look at here, it's not written with any subindex here because there is nothing to decompose on this force. So we could say that with the reference system we are using at the moment, which intuitively or let's say tacitly said is just this one, xy, you don't need to decompose any force AB at all because it's lying on the x-axis here. So that's why it doesn't have any subindex here, x or y or anything. Now, in the vertical direction, of course, you have that BC is pointing towards a negative direction, and then DB is pointing toward the positive direction. And that's why you have it represented in this form here. Again, if I make, let's say, an inventory of unknowns to this point, well, I don't know how much is the magnitude of BC. I don't know how much is the magnitude of AB. I do know how much is the magnitude of DB because it's about BA. Sorry, I know the magnitude of BC. I don't know the magnitude of BC. I don't know the magnitude of BA. I do know the magnitude of DB because it's given here as 3.5 kilonewtons. Then still two unknowns, two equations. If we substitute all the known values on those equations of equilibrium, we're going to end up with something like this. And let me move forward a little bit. And the good thing of, look at this. So I have the equation of equilibrium. We substituted all the known values that we are given from the problem. And then when we inspect, for example, this equation, we notice that there is one equation and one unknown, meaning that from this equation, I can already know what's the value of this magnitude, FBC. And actually, if you just isolate or solve for this FBC, you're going to get an answer right away saying that, hey, the magnitude of this force here, FBC, equals to this 2,990 newtons. Right away. And you're going to notice if you're able to start seeing the patterns on these type of exercises and also in real life applications, things get pretty much easier when one of the forces you want to, let's say, solve for or investigate or something like that aligns with one of the axes of the reference system. So in this case, force AB aligns with the x-axis of our reference system, and that simplifies a lot, let's say, the solution of our problems here, because you know already that there is not going to be the presence of this force AB in the vertical direction. And then that's why is the way this is constructed enables us to just find an answer in a couple of steps here. Now, what I want you to take as a pointer here is that if you can always find a reference system that aligns with one of your, let's call it problematic forces, because you don't know what's the magnitude of it, that would simplify the problem very, very much. Now that we have found the value of the force BC, what we do? Well, definitely, now that we have found this value, just put it in this first equation here, and you can solve for this one here. Let's look at that. Here it is. And then you have the other answer, meaning that you have this force here pointing in this direction of 3.78 kilonewtons, this one here of 2.99 kilonewtons, and this one here of 3.5 kilonewtons. And for this configuration that we have right now, under this loading case, that system is in equilibrium. And again, the only way we can know that is because, even though it was not written in the description of the problem, we're talking about equilibrium of a particle. Hence, all of this is possible because of that. What questions do you have? Let's see another type of problems that they can present to us. And this is also pretty interesting. And again, the complexity, say, increases a notch here. So we have a cylinder pipe, hanging. They're using a rope to, let's say, to lift this pipe or piece of pipe or segment of pipe. And it says, yes, of course, AB and AC can sustain a maximum tension of 8,000 newtons. So it means that the tension, when we call tension, is that imagine that you have, just for the sake of, imagine that you have a rope and you have 2 knots here. If you pull this knot in this direction, and then you pull this knot in this direction, the force in the body of this segment here is going to be, let's say, exposed or extended, or what's happening there is that this body is going to be in tension. It's when you try to break 2 things apart. Then the same concept applies here, that in this segment here, when a force applied to try to produce tension on this segment, if that force is over 8,000 newtons, then this will break. Now, this is a problem that also is pointing at a design problem, because when we design elements or physical elements, so we need to find out what are the forces, what is the geometry, what is the material we're going to use, so the machine does not break. And it does that. We want that machine to do the work, or the element or the piece or something part of a mechanism. So you say, well, you know what? If the tension force in this segment or in this segment is larger than 8,000 newtons, it's going to break, and we don't want that. We know that the drum, we call it drum here, weighs 9 kilonewtons, and they're asking us, okay, if we wanted to suspend this, to lift this using a rope, what is the minimum angle that should exist here so that these segments don't break? That's a question. So apparently there, or not apparently, but obviously the first unknown that I need to figure out, to give answer to or figure out, is what's the value of this angle theta. So that's something that I don't know. But then you might be kind of thinking, okay, but what about what's the real tension of this? Because I do know that this has a weight of 9 kilonewtons, but I don't know what is affecting here. So what should I do now? So how many unknowns will I be able to solve this problem? Well, let's follow the steps and let's do the first thing we need to do all the time, which is let's draw the free body diagram of this case here. Yeah, it's pretty simple. So in terms of free body diagram, it's pretty simple, not because the problem is simple, but because of the symmetry of the whole conditions that are happening here. So you have the tension of this rope. There's a tension here, T. Then there are these 2 forces, which are the forces on the segments AB and AC here. And again, because of the symmetry, the orientation of these forces with respect to the x-axis is the same, an angle theta. And without knowing too much about engineering or anything like that, we may be suspecting that that there are certain similitudes between FAB and FAC because of symmetry condition. If I have these 2 forces, so are these magnitude different, or what's happening here? So, but let's continue. Now, if let's remember, so the free body diagram is drawn taking this knot in A as a particle. So I don't care about the drum. You see, that's a beautiful thing about free body diagrams, that you isolate, just the segment you want to study. And you forget if this is a drum, this is a pipe, this is a car, or anything, you forget about that because you are only interested in this small piece of the reality, that one, and what is coming to it in terms of forces. So that's why you say, well, you're talking that the drum has a weight of 9,000 kilonewtons, but why the weight is not represented as going downwards? Well, because actually the weight of the drum belongs to the drum. No, it doesn't belong to the knot A. So yes, the weight of the drum is going to be represented somehow in this tension T, but that's why it doesn't go downwards, because the drum does not exist anymore in this free body diagram. Let's imagine that the effect of the weight of the drum was translated to what this has to hold. That's why it is like that. Now, if and look at this, so we always start with equilibrium in the x direction. So why we didn't start in the equilibrium in the x direction here? So we are starting with equilibrium in y direction instead of the x. Why is that? Well, if you make the equilibrium in x direction, you're going to find out something pretty, say, evident. And that is that, for example, FAC cosine of theta positive minus this one here, FAB cosine of theta equals 0, because this particle is equilibrium. If you manipulate this a little bit, you're going to find out that simply the FAC equals to FAB. So they are the same magnitude. They have the same magnitude. Now, this is a second pointer in general for engineering. So symmetry conditions can simplify our life pretty much in terms of design. And this is one evidence of it. The other pointer is that, as I mentioned here, going back, if you can orient your reference system so that again, I'm going to call it problematic force, the force you want to find out, aligns with one of the axes of that reference system, it would make also your life easier. So 2 pointers here, in general, as from an engineering standpoint. Symmetry is always good. It simplifies a lot. Now let's continue. So equilibrium, the equilibrium condition, well, equation in y direction is this one, pretty obvious because I have these 2 vertical components going downwards. So this is FACY, and then this is FABY, which is also represented by taking the magnitude and multiplying by the sine of this angle, in both cases. Due to symmetry, as demonstrated before, FAB equals to FAC, and then you could use, so he uses irrespectively or any of those, well, this nomenclature here. So that's why this equation here is transformed to this equation here because this value and this value are the same. So if you group these 2 values, common term, and then you just sum these two magnitudes or these 2 quantities are the same, you're going to find out that T equals T minus 2 FA sine of theta equals 0, thanks to the symmetry conditions. Now, we come from here. Well, let me try to see if I can copy this equation because this is interesting to have. Do I have it here? Yeah, that's what I have. So, okay, so now I ended up with one equation, this one. I don't have more equations to work with, so this is my only chance. I have 2 equations, and apparently I'm having 2 unknowns. The magnitude of FAB and the magnitude of the angle theta. So how can I solve this? How can I approach this problem? Because, well, I know that T is 9,000 or 9 kilonewtons because of the problem description. But how much is FAB? Because they're asking for the angle, so how much is FAB? Well, it's not given, but what is given is a design condition. And the design condition is that, yes, this segment, the tension force of this segment should not exceed this 8,000 newtons. So if this is a design criteria, meaning that that's what's going to dictate how the design is going to go, then I need to certify or to guarantee that in my calculations, the tension forces in the segment AB and AC do not, let's say, exceed those 8,000. And to guarantee that, I might use this 8,000 Newton as limiting value for FAB. And that's why here, this 8,000 Newton is included instead of this FAB, because we are saying, you know what? Yeah, I don't know how much it's going to be this, but what I don't want is that the magnitude of this force exceeds these 8,000 Newtons. So let me plug in 8,000 Newtons here and see what's the result or what's the angle that I need to use. So this is in the limit. So this is not going to exceed this 8,000 Newtons. So that's why we are using this value here, just as a design condition. Then if we just take this angle theta and solve it, take the inverse of the sine and this simple trigonometric relation, so we find that, you know what? If you don't want to have more than 8,000 Newtons in these segments, so don't use an angle smaller than 34 degrees. But let me move a little more. Yeah. So again, we were not given at once the magnitude of these segments, but we were given a design condition that we need to, let's say, abide. We need to comply with. So, pretty interesting problem. What questions do you have? All right. It's getting interesting. Let's see this one. Now, this is another variant that we can find. In this case, let's say, it looks similar to what we have done in the past. But in this case, when you read the description of the problem, it says, determine the force in cables AB and AC necessary to support a 12 kilogram traffic light. So we have a traffic light here, and it says that 12 kilogram traffic light. This is not a unit of force. And when we are given these 12 kilograms, we automatically have to recognize that, hey, this is not a unit of force. I need to transform this into a force unit. And basically, we're talking about weight, which means that I would need to, at some point in my calculations, multiply this by the value of the gravity, which we might be probably using all the time, this 9.81 meters per square second. Then times this mass here, or measurement of mass, it would give me 8 newtons, basically. So this is something to be, let's say, keep an eye on. Then they want me to find the magnitudes of this force of this segment here, definitely because I want to have a weight here of the traffic light, this force AB, and then we're going to have a force AC here. And yet, well, we're talking about determining the forces, these two forces, already 1 and 2. So meaning determining the magnitude of these forces, because the orientation is already given. See here, for example, the orientation or the angle that this force forms with respect to the x-axis is 12 degrees. And then the orientation or the angle that this force forms with the x angle, then you can calculate it using these relationships here. Also, we are given in this problem one of the two forms that we could use to represent, let's say, an angle or an orientation of a force with respect to the axis of the reference system. First, free body diagram. That's the first step. We always need to start with the free body diagram. That's something we need to emphasize. You don't start with anything. First, draw the free body diagram. And then we're taking that node A is considered as a particle, and see, yeah, we have the traffic light, but as we made a cut here, that traffic light, it doesn't exist for us anymore. These poles don't exist for us anymore because they are taken out of the equation during the isolation process. They don't exist anymore. The effect of those elements do exist in the free body diagram, and they are representing the free body diagram, but the physical representation of them disappears. Then we have FAB, FAC, the angle that forms FAB with the x-axis, and then the weight. Let's continue. Nothing new so far. Again, this is not in symmetry, or we might assume that these two inclined segments are in symmetry because they don't seem, well, by the figure doesn't seem so. And definitely, if we calculate this angle here, they might not be. That's why we cannot, make use of this symmetry condition of saying, well, as these symmetries are in symmetry, then FAC equals FAB, and everything is simple. Not this case. So here we have to recognize that, if we sum forces with respect to the x in the x direction, I know that FAB is going to be positive, and the component of x of FAC in the x direction is going to be negative. That's why it appears like that. And in the vertical axis, I know that these two forces are going to say produce vertical components in the positive direction. That's why you have it positive here and positive here. And then when you have this vertical axis here, then this weight is pointing downward. Then this is in negative direction. That's why it's represented. So let's then substitute, I think, what we know. So we know angles. We already know how to use this triangle representation to calculate the orientation of angles with respect to the coordinate axis. And so that's why in the x direction we have a cosine, FAB cosine of 12 minus this 24 divided by 25 times f. So if I want to know the angle, again, as a refresher, the angle of this curve with respect to the x-axis, this one here, then I have to use this adjacent side divided by this hypotenuse here. Then when we do the same for the vertical axis or the y direction, then we're going to have the three components. And this is where I mentioned to you that you have to be careful of this. Yeah. So this says that, okay, yes, you are giving me a something, a weight, but this is not represented in force units. So I need to transform this into, from mass to force units. So something. Then let's make an account of how many unknowns we have so far. So we have for sure two equations, product of these, these two components, or the decomposition of forces. But if I want to account for the unknowns, so I know that I don't know FAB, I don't know FAC, well, they repeat here. So I have two equations and two unknowns. So it means that most probably I would be able to solve this. Let's continue. Right. So again, we could use substitution in this case to try to solve for these two unknowns. So the first thing we can do is that, well, if I take this equation 1 and I isolate the value of the magnitude of the force AB, then this could be written something like this. And then what we do, well, it's not seen here, but we can input the value of this FAB in this position here. And if we do that, you're going to have this one. So being this, the value of FAB. And then the rest of the equation stays the same. If you continue kind of simplifying this, you're going to find out that now this equation on top depends on FAC and, well, the same FAC. So we could isolate this FAC and solve for it to see what's the value, because that's the only unknown I'm having here. So having that, it turns out that FAC equals to 243 newtons. And then what should we do? Well, logically, if I already know what's the value of FAC, I can come back here, input it here, and then that would give me the value of FAB right away. Let's jump to the next slide. And here it is. So this kind of the answer to the question that we're asked there. So what are the magnitudes of the forcing cables AB and AC? And see how it's postulated, kind of forcing cables AB and AC. So that means magnitude. Doesn't mean anything as a magnitude of those forces. And that's what is being solved here. What questions do you have? Just any though. All right. Let's see the fifth example, and I think this is the latest example. Yeah. So now it says, we have a flower pot very supported by two ropes. And it says that, again, let me read it because it's pretty similar to the previous one. It says, determine the maximum mass of the flower pot that can be supported without exceeding a cable tension of 250 newtons in either cable AB or AC. And now look at this. So they're asking me basically not the weight of the flower pot. They're asking me the mass of the flower pot. So this means that when I do my whole procedure of starting with the free body diagram, decomposing forces, solving the system of equation after applying equilibrium and everything, I might end up with a force result. But that force, I need to transform it into mass. And again, if I take the weight, it's going to be equal to the mass times, the gravity value, which we are using, again, 9.81 meters per square. Yeah. So the final answer is not the weight, it's the mass. And then we have a design condition. That is that the tension, I remember the concept of tension here, in either of these cables should not exceed these 250 newtons. So then we are not given any specific magnitude, but we are given a design condition. Unfortunately, as this is represented right now, this is not symmetric, non-symmetrical problem, meaning that it doesn't resemble the one with the drum suspended in the air. Yeah. And imagine that. So we are not giving any information about the magnitude or anything like that. But it doesn't matter. So far I cannot spot how many unknowns do I have. Well, for sure I don't know the weight of the flower pot, because definitely that's one unknown, this one here. But what other unknown do I have here? Well, I will know. So I have 3 unknowns actually, because I don't know this, the forces here. I don't know the force here. So I'm having 3 unknowns. But what should I do? So far I cannot see clearly that it's going to be a solvable problem. But in any case, we need to take the first step. And the first step is to draw the free body diagram. Let's do it. Again, the angles are represented as, as degrees or as this triangle here. By the way, whenever you find a triangle like this one, with sides 3, 4, always note this side, the kind of the hypotenuse here is going to be always 5, always 3, 4, 5. This is something that always you don't have to calculate anything. If you have kind of 3 and 4, this is going to be 5 all the time. Free body diagram. So again, the initial angle represented for the segment AC is with respect to the vertical axis, but we want it to be with the horizontal axis because we're considering that this is the x-axis. And the complement of this angle here, this rectangle angle. Just a second. I'm going to answer that question right now. So this complement is going to be 60 degrees because this one is 90 degrees. Now there is a question that, how do we use a rectangle here? Actually, the question is, how do we use a triangle? Yeah, let me see. So the way you use this triangle is, if you want to know this angle here, let's call it alpha. Well, alpha is going to be what? Alpha is going to be equal to cosine of 3 divided by 5, something like that. Yeah. And if you want to know kind of what is this angle over here, 3 divided by 5. Yeah. Let me see. I don't have it. Yeah. I kind of missed the point here that I was trying to explain later. So when we derive equations of, for example, of forces here, we try to explain it this way. When you have a force here, and you want to know what's the component of this force with respect to the horizontal axis here. Yeah. So this component is going to be, say, Fx is going to be what? F value times the cosine of alpha. Yeah. Alpha is going to be what? Actually, to try to find out alpha here is basically the inverse of the cosine of 3 divided by 5. So if you want to know this angle here, is basically kind of the inverse of the cosine of this divided by, because the cosine of alpha, if you want to put it that way, is 3 divided by 5. Adjacent catet, I believe that's the correct pronunciation. The adjacent catet divided by the hypotenuse is going to give you the cosine of alpha. So if this thing is here, is this one here, then you can just write that the f in x equals f times 3 divided by 5, by the way. So the way you use the triangle is like that. So you don't have to use any cosine or sine. You just, if you want to find the equivalent of the cosine, for example, you use the length of that catet here, and then the hypotenuse, and then if you want to find the cosine, you use the opposed catet, and then the hypotenuse to find the vertical direction, like this, times 4 divided by 5. Does it make sense? I hope so. Okay, so we are here. Again, we were saying that we need to use a complement of this angle here. Then if we form the equation of equilibrium, in the horizontal axis, we're going to have that, well, the x component of this force is positive, the x component of this force is negative. And both vertical components are positive. Gravity doesn't have any component on the x-axis, only have a negative component in the vertical axis or y-axis. Then that's why it doesn't appear in the y form, the sum of forces in the y direction. So then we have here that the force AC times cosine of 60 minus, because this is pointed in the opposite direction, is 3 divided by 5 FAB. So again, actually triangles make it a little bit easier to apply formulas here, because we don't need to calculate anything like that one, or is visible, more appealing, say. Then in the vertical direction, we have both positive, both terms positive, and the gravity negative. So let's make an account of the number of unknowns we have here. We delete this. I don't know how much is the force AC in the segment AC. I definitely don't know what's the force in segment AB. They repeat here, and I don't know how much is the weight, because actually that's kind of part of the answer they are asking from me. So I'm having 2 equations and 3 unknowns. So this system is definitely, at this point and how it is presented, not solvable. So we need to work a little bit more to find out hidden relationships between them. So let's take the first equation, the component sum of forces in the x-axis. This one here. So if we put any kind of those magnitudes, FAC and FAB, in each part of the equal sign of the equation, like this one here, and working a little bit with kind of the cosine of 60 is, well, it said that it's 1/2, 0.5, and then, if you do a little bit of mathematical operations on that equation, you're going to end up with this equation at the bottom here. But what is this saying to us? Or what is this trying to communicate to us? This said, the force in segment AB, this one here, is 5/6 of the force in segment AC. So it means that if I have a force in AC and this value 5 divided by 6 is smaller than 1. If I have a force in AC and I reduce it because I multiply it by a value less than 1 or smaller than 1, I'm going to have the value of the force in the segment AB, meaning that force, as is written I believe later, the force in the segment AC is larger than the force in the segment AB. And then if the force in AC is larger than in the other one, from a design standpoint, I need to be careful that the largest force does not reach the 250 Newton first. So that's why I can confidently say, well, I don't know the values, but what I do know is that this force here cannot exceed 250 Newton. And to verify that, or to guarantee that across the solution of the problem, I can input the value of 200 Newtons as a value for FAC, and then continue solving everything. Then what I'm going to have here then? So if I have this 250 Newtons, so now I know that I'm going to be considering as a design criterion that FAB is going to be 5 divided by 6 times 250, which is represented here. See, I'm now working with equation number 2, this one here. So this is now FAC, the value, but all of this is FAB. Then I just multiplied by, yes, I will repeat that in a moment, just a second. I multiplied that by, the value that I assume for FAC, and then this value. Then what is left is the value of the mass now that I don't know, that I could solve for. Before doing that, so we got a question in the chat that says, can you repeat the explanation for the relationship between FAC and FAB? Yeah. Let me start by this part here. So I don't know which would be the most convenient, but if we look at this equation here, definitely, well, I know that from this equation, I can get to this one. I hope that that's kind of clear. It's just substituting this cosine of 60 by 1/2, and that's it. So we put this to the other side, and then, we just isolate each one of those. So if you work in this way, do a little bit of mathematical manipulation of this, you're going to end up with this equation here, that FAB equals to 5/6 of FAC. So meaning that FAB is FAC multiplied by something. But this something here is smaller than 1. And if it is smaller than 1, everything that you multiply for here is going to be reduced. So let's do an example. So if I say that FAC equals 1, FAB is going to be equal to 5 divided by 6 times 1. So FAB equals to 5/6. Yeah. Then if I compare the values of FAB and FAC, I'm going to notice that FAC is always going to be larger than FAB, because the very same equation is telling me, if you want to know the value of FAB, take a force represented as FAC and multiply it by a value which in this case is smaller than 1, and always you're going to have that FAB is going to be smaller than FAC. Then if this is the case, that FAC is going to be larger than FAB, if I am applying weight here in the flower pot, meaning if I'm increasing the weight of the flower pot constantly, FAC is going to be always larger than FAB. And then the more weight I applied here, the larger FAC is going to be, and this is always going to be smaller than FAC. So which is going to reach the 250 newtons first? If I keep increasing the weight here. If I increase this weight from 0 to 200, to something, 1,000 newtons, an exaggeration. When I'm increasing this weight from 0 to 1,000 newtons, this force is the first that is going to reach the 250 newtons. Because when this force is 250 newtons, let me do a quick calculation. FAB is going to be, we just multiply 250 times 5 divided by 6. It's going to be 208. Let me write it here. It's going to be 208 newtons. You see? So when this force FAC reaches 250 newtons, this still is going to be less than the limit that is being imposed here. So that's why I can say, you know what? Now, I don't know the value of those two magnitudes, but if I want to make sure that the tensions on those cables are not going to exceed the design criterion here of 250 newtons, what I can say is that, you know what? What would happen then when this force reaches to the limit, this FAC reaches to 250 newtons? What happens with the rest of the whole elements? What happens with FAB? What happens with the weight of the flower pot? Hence, what happens with the mass of the flower pot? And that's the relationship between those two forces, FAC and FAB. I hope it is a little bit clearer now. If it is, well, great, thank you. Now, if we solve for this term here, knowing that the mass, the gravity is 9.81, so I can isolate this mass here, and the mass is 39 kilograms. Remember, we've been asked the mass in the mass of the flower pot, not the weight. That's why we are returning this answer as kilograms, not newtons here. And this is the last slide for this one. What questions do you have? For the homework, using a programmable was allowed, or did I misunderstood? That's a question from the chat. I think you can use it. I still think that many that the answers that you are going to provide, one of the specific purposes of the whole, or how only Pekka has everything set up is that they would like you to write things, to derive things analytical, pen and paper, and that means that at some point I think you can use. I can ask about that also, as the question was let's say asked before. But let me see to which extent you could you could use straightaway answers. I don't think that just coming with an answer, direct answer to everything without writing that much is possible. But definitely programmable, let's say, calculators are useful. I will verify that, because so far I don't think you have been using you haven't had the need of using any let's say smart calculators, programmable calculator for the past exercises. But for this one, there are a couple of let's say exercises that might be needed that you need to, they are a bit more complex, so meaning that you have to write a little bit more, but all of them are solvable by just writing, using pen and paper. Definitely they are easier. It is easier if you use this programmable calculator, but most of the exercises given to you are solvable with pen and paper. One would take longer. They would require a little more of manipulation or understanding, but definitely all of them can be solved with pen and paper. It would take some time. What I do know is that, he mentioned, is that for the exam, there is nothing on the exam that you would really need to have a programmable calculator to solve the exam. So no worries about that. All right, so let's see. Great. Let's jump in the few minutes we have left to what you're going to be presented in the recordings we're going to have available after this class, which are the demo lectures here. And let me switch to it so you can notice that, you're going to have a recording of how to solve these exercises. Just notice something. The way they are solved, they are not unique, so you can find different ways to do it. And for example, you have now in the two first examples, you're going to be, let's say, solving not as an exercise, but as a solved recorded exercise. You're going to be using springs, what I mentioned in the first two, and the third one is a rope. It's a very interesting one. So for this first one, remember we mentioned that springs, and when we talk about springs, we talk about the force of a spring. For example, in this case, AB equals to K times S. Let's call it AB, and then K, the stiffness coefficient of these springs are given. And look at this. They don't need to be the same. Yeah, they don't need to be the same. But the important thing is that is given there. And kind of the description of the problem is determine the stretch in each spring for equilibrium of the 2 kilograms block. The springs are shown in the equilibrium position. So how to start this type of problem? So first, when we are in the presence of springs, we need to understand something, that springs might be in the rest position or resting position, or they might be in the stretched position. You need to consider that. So they may be either resting position or at rest, or in the stretch position. In this case, when you read the description of the problem, it says, are shown in the equilibrium position. It means that this was, at some point, it might be that this was something like this. Imagine this, and then you have this one here, and then you have and you were holding that whole system with, I'm going to try to draw a hand. That's a bad hand, but you get it. So this hand. You were holding that block. And this was, these springs were in the resting position. So when you release the whole thing, so you remove your hand, because of the weight of the block, everything fell down until it found an equilibrium position, meaning where, the forces exerted by each of the springs, got to a negotiation and said, you know what, we're comfortable in this position, let's call it equilibrium position. Then it is not written in the description of the problem that they are in the stretch position. They said that they are in the equilibrium position, but that's equivalent to say that they are in the stretch position, because all the forces acting on the system made the springs stretch to a point where they found equilibrium. And then what they're asking is, okay, now determine the stretch in each spring, meaning that if the force in AB equals KAB times SAB, force in AD equal KAD times SAD, and also, well, you already know the third one, FAC equals KAC times SAC. They're asking us how much is this one, and this one for this configuration. Okay, so I need to know that one. But then, to know that one, it means that I need to know how much are these forces, because the stiffness coefficient K are given for each one of the springs. And then if I need to know these forces, what should I do first? Well, you must do your free body diagram of this element. And kind of, you start from there. A few minutes still. This is pretty interesting. This is the contrary of the first one. It says, the 45 newtons lamp fixture is suspended from two springs. So this lamp fixture is 45 newtons. And of course, it's pointing down. It says, each having this is a mistake, unstretched length of 1.2 meters and a stiffness of 75 newtons per meter. Determine the angle theta for equilibrium, meaning that these springs are stretched, and you don't know how much they are stretched. You do know that definitely if the unstretched length was 1.2 meters, it means that these springs were here before releasing, everything. And then you had here the lamp picture. Then there was a hand. Then you released, let me try to erase it. So you release the hand, all of this, and then when everything fell down because of the weight of the lamp fixture, then, they came to a negotiation and said, you know what, now we are in equilibrium, let's stay like that. So the spring stretched to a point here that you don't know how much it is. Now the question is, what is the angle? Now they are in equilibrium. And again, to know the stretch here, you know that the force in this one here is K times the stretch, and also the force in this one is equal to K, the coefficient of stiffness coefficient times the stretch. And the beauty of all of this is that this is a symmetrical system, which means that this force here equals to this one, which is going to give your head is all of this. Finally, the third example is more or less similar to the ones we have done before. The only consideration that I'm going to leave you with is that when we're talking about a pulley here, the tension in this cable here, tension, let's call it, or force CA and the force DA are the same. When we talk about pulleys, this always happen. What questions do you have? Let's close now here. Oh, yeah. Yeah, I believe they are going to come this week. Yeah, definitely are going to be open to be reviewed and then to check your own answers with the answer key for the weekly exercises. Be able to move them. Yeah, I think they're going to be published this week. So you will have access to check everything. So definitely they are released after let's say, everybody, the deadline. Another question we have is, could you please repeat why are those forces the same? It comes from a pulley property, actually. Let me come back to it. So in a pulley, when you talk about pulleys are, these circular members or elements. Let me draw another small one. This is the center of rotation or something like that. Then when you have two forces on a pulley, imagine then as, for example, you have one force here and you have another force here. Yeah. Imagine that the force you apply here, it just comes, translate completely over the whole side and then, communicates with this one. So, but that comes from something called a modification of the Newton's second law, but for rotation. And then, it is demonstrated that the tension in both sides is the same. But it comes from, that we have shown that force equals to mass times acceleration. There is another a change to this law. It's called the second law of mechanics. So it's called that the sum of moments around a point equals to moment of inertia times something, the angular acceleration plus something else, depending on the case. So using this in such system, it's demonstrated that these two tensions are the same. That's the short, unexplained answer. Well, thank you very much. It was nice to have you, and have a nice week. I'll see you next week with another topic. Take care. Bye.